G'day, let's talk about stereochemistry and stereoisomers. Stereochemistry is about the three-dimensional arrangement of atoms within a molecule. So whereas constitutional isomers differ in the way that the atoms are connected to each other, so we might have C5H10 might be cyclopentane, or it might be 1-pentene. So they have the same molecular formula but a different connectivity of atoms. Stereoisomers have the same connectivity of atoms, but a different three-dimensional arrangement. And they fall within the whole umbrella of isomers. So within isomers, there's conformational isomers, which we are treating as being a different branch altogether. Constitutional isomers, where we have different connectivity, and stereoisomers, where there's a different three-dimensional arrangement. And they can be broken down into other subgroups as well. We'll focus on enantiomers during this video. So the stereochemistry of geometric isomers is really about three-dimensional arrangement of atoms in molecules like cyclic molecules, where we can get both groups on the same side, which would be a cis isomer, or on opposite sides of a ring, which would be the trans isomer. We also have acyclic molecules, where we've got a down bond, and here we've got an up bond. So that would be different too if they are both down or both up. Now, when we talk about these cycloalkanes, the geometric isomers, really there's just the possibility of cis and trans when we have two groups. So if they're both on the same side, that would be cis. If they're on opposite sides, that would be trans. Now let's compare that to a situation known as optical isomers or enantiomers. So molecules A and B here are mirror images of each other, but they're special mirror images. They're mirror images that aren't superimposable. And one of the classic examples of an object in everyday life that is a non-superimposable mirror image of its counterpart is your left hand versus your right hand. So your two hands are mirror images of each other, but they're not superimposable. In other words, I can't put one on top of the other and end up with them both being the same. However, they are mirror images of each other. So molecules of that type that are non-superposable mirror images, we call them chiral molecules. And more generally, objects that are like this, that are non-superimposable mirror images, are chiral objects. And so your hands are actually chiral objects. The two mirror images of chiral objects, or chiral molecules in the case of chemistry, we call them enantiomers. So one is an enantiomer of the other. So my left hand would be one enantiomer, and my right hand would be the other enantiomer. Now, most chiral molecules have what we call a chiral center, which is closely related to the term stereogenic center. In carbon chemistry, or the chemistry of organic molecules, really this comes about when we have four different substituents around a carbon atom. So this idea of chirality is really important, and it really is important about to spot chiral atoms within a molecule so you can tell whether those molecules are chiral or not, and to say something about their stereochemistry. So what we need to do is look at Kekulé or line bond structures of molecules and be able to spot where there are four different substituents attached to a carbon atom. So for example, if we look at this molecule here, the carbon that's in black here is a stereogenic carbon atom because it has a hydrogen, a carbon, and then has this carbon is different to this carbon. So those two groups are different enough that central black carbon there has four different groups attached to it, and therefore it's a stereogenic or chiral carbon atom. Now it turns out that the one next door to it, this green one, is also a chiral carbon atom. It has a hydrogen, not drawn in, a methyl group, this chain over here, and this chain over here, which are different to each other. So four different groups. And so this molecule actually has two stereogenic or chiral carbon atoms. So I have an asterisk there. Now, lots of pharmaceutical compounds are chiral. So for example, ethambutol is an antibacterial reagent that is used to treat tuberculosis. And it is this compound here, and it's chiral. It has two chiral centers that are shown in these circles here. So one enantiomer of this molecule, ethambutol, is used to treat tuberculosis, but the other one actually causes blindness. So it's important that we know which one is which, and we can prescribe just the useful one and not the harmful one. So let's look at symmetry in molecules and how this relates to chirality. So if we look at these examples here, we've got two mirror image molecules and a mirror plane between them. And we want to know whether the molecule is chiral. So there's a few rules that must be satisfied for a molecule to be chiral. It must have be three-dimensional. It must have no plane of symmetry. So achiral molecules, or achiral meaning not chiral, contain a plane of symmetry. It's possible also for a achiral molecule to contain stereogenic or chiral centers. So we may actually have chiral carbon atoms that have 4 different substituents, but for the overall molecule to have a plane of symmetry and therefore be achiral, and its mirror image to be the same as itself, in other words, superposable. Okay, so if you look at the examples here, we've got a chiral molecule with 4 different substituents. That molecule has no plane of symmetry. If we look at an achiral molecule, so an achiral molecule with a carbon atom with 3 different substituents means that 2 of them are the same. So we've got 2 yellow atoms here that are the same as each other. And because 2 substituents are the same, there's a mirror plane or a symmetry plane going down the middle of the molecule. And having a plane of symmetry is enough to make sure that the molecule is not going to be chiral. Okay, so one really important property of chiral molecules is that they do something interesting to plane polarized light. So plane polarized light is where we get normal light, we pass it through a polarizing filter, and we only have light that is sort of vibrating in one plane. So we call that plane polarized light. When we pass that plane polarized light through one enantiomer of a chiral molecule, we find that it actually rotates the plane of polarization of that light. And so one enantiomer will bend the plane polarized light in one direction, for example, clockwise, whereas the other enantiomer will bend the plane polarized light in the opposite direction, anti-clockwise. So that's anti-clockwise for me. Maybe for you as the viewer, it's clockwise. So the one enantiomer always bends the light in the opposite direction to the other enantiomer. So in order to quantify the observed rotation, we actually need to know how much of the sample we are passing the light through. Because obviously if you have more molecules in the solution that the light is interacting with, we get more opportunity for that light to be rotated through that angle. And so we can actually measure a quantity known as the specific rotation, which is this term alpha that we put in square brackets. So the specific rotation at a particular temperature, T, and at a particular wavelength, lambda, is the observed rotation, how much we actually see that plane polarized light being rotated, divided by the length of the cell through which we're passing the light, and the concentration of the sample. And unfortunately for this measurement, for historical reasons, we use unusual units. So the length we use is actually in decimeters, and the concentration is in grams per mil. So experimentally, how this is determined is we get a light source, we plane polarize it with a filter here, we pass it through our solution, that bends the light through some kind of amount of rotation, and then we measure it with another polarizing filter that we can adjust the angle of. At what angle do we get the most light going through that filter? And that allows us to measure the angle of the rotation. This is a very old polarimeter, the device we can use to measure this in a sample. Okay, so optical rotation, these measurements have been done for many, many decades for many compounds. And historically, if the plane polarized light was rotated in a clockwise direction, we call that positive rotation, and we give it the symbol D as well, which stands for dextrorotatory, from the Greek dextro. If it rotates plane polarized light anti-clockwise, for me that's anti-clockwise, then we call that the minus isomer or enantiomer, and we say that that's levorotatory, from the Greek levo for left. So it turns out if we have an equal amount of both the plus and the minus, or the D and the L isomers, we call that a racemic mixture. And racemates, or racemic mixtures, are really common in organic chemistry. And so they have this special name. And because we have equal amounts of substance that's one is bending light one way and one is bending light the other way, they cancel each other out. So overall, a racemate has an observed rotation of 0 degrees. And usually we use the symbols DL, because there's an equal amount of both the D and the L, or plus minus to talk about racemates. Also, in more modern times, we use the abbreviation RAC, RAC, to say that something is a racemate. So let's look at some molecules and see whether they're chiral or not, or achiral. So 2-butanol, if we look at this molecule, and we bring up the mirror image here, and we put a mirror plane between the two of them, then we can see whether they are superposable or not. And this becomes really much easier to see if you actually make the models, put one model next to its mirror image, and then try to overlap them, and you'll see whether something is superposable or not quite easily with models. In this case, 2-butanol, the mirror image is not superposable with what we drew in the first place, and so the molecule is chiral. And there's the chiral center. We have 4 different substituents around that carbon atom in this molecule. So there's yet another term that's used to talk about chiral or stereogenic centers, and that is an asymmetric center. So you'll see all of these terms being used in various places depending on the textbook and the lecturer and so on. Okay, let's look at a related molecule. What about 2-butanone? Here we've got 2-butanone drawn out on the left as viewed from sort of the side as we draw it like this. And then we've got it also drawn where we rotate through a 90-degree angle. So we're looking at it edge on. So sort of imagine your eye being up here and looking down upon the molecule like this. So here is the carbon atom, and hopefully there is the carbon atom with the carbonyl group attached to it. And hopefully you can see that there's a mirror plane of symmetry going right through the molecule as we're looking at it end on. And so therefore this molecule is not chiral. It's anything with a mirror plane is achiral, and therefore the mirror image is the same as itself. So they're superposable mirror images. So 2-butanone is achiral. I've been using this term for a little while now, but I'll just define it. Chiral compounds and their mirror image are called enantiomers of each other. So one handedness or one mirror image is going to be one enantiomer, and the other mirror image is going to be the other enantiomer. So if we're talking about objects, we would say that your left hand is an enantiomer of your right hand, or your left and right hands are enantiomers. So for 2-butanol, the 2 isomers we've drawn there are enantiomers. Here's another molecule that is chiral. It's called asparagine, and it's from a plant source. It's from the asparagus plant, which you may have eaten. So asparagine has a bit of a bitter taste and adds to the flavour of asparagus, but only in the natural form, which is present in asparagus itself, which is this particular enantiomer. The mirror image, or the enantiomer of asparagine, is this one here, which is known as D-asparagine, which is from a different plant and actually has a sweet taste. So in your body, things like your taste receptors and your smell receptors can sense the difference between chiral molecules. One enantiomer will have a different taste or smell to the other enantiomer. And similarly, in pharmaceuticals, one enantiomer can have a very big difference in its biological properties compared to the other enantiomer. Camphor is a molecule that is isolated from trees, and it comes in 2 different forms. The one on the left there and the one on the right are enantiomers of each other. So that's an example of a more complex molecule where we have 2 different mirror image forms that are not superimposable and therefore are enantiomers of each other. A very famous, unfortunately infamous case of stereochemistry and its importance is the story of thalidomide. So thalidomide was introduced as a drug to treat morning sickness amongst pregnant women in around the 1950s, late 1950s into the early 60s. It was only sold for a period of about 4 years or so in the US and some other periods of time in other countries. And it was withdrawn soon after that because it was quickly realized that thalidomide was causing birth defects amongst the women who were taking the drug for morning sickness during their pregnancy, and then they were giving birth to babies with malformed limbs. So very much shortened limbs, sometimes missing entire limbs, or very, very shortened arms, legs, feet, and so on. It's actually only one enantiomer of the molecule that causes the birth defects. However, unfortunately, in the body, the molecule undergoes racemization. So remember we talked about racemates being a mixture of both enantiomers. So even if we get thalidomide as the biologically active, non-teratogenic, which is birth defect causing, as the sort of safe molecule, if we give that to pregnant women, it actually converts in the body to a one-to-one mixture of both enantiomers. And so we get some of the harmful teratogenic molecule being formed within the body. And so we cannot use the drug in anyone who is at any risk or any likelihood of becoming pregnant during the treatment with the drug. So it was banned for a very long time, and it's actually come back into treatment to treat certain diseases. Some cancers, particularly some leukemias, and leprosy can be treated with thalidomide. So thalidomide is only prescribed under very controlled circumstances, only to men or to women who are not going to fall pregnant during its use. But really, the thalidomide case is what led to really strict controls being put on what pharmaceuticals are available and how pharmaceuticals are tested. So before thalidomide, pharmaceuticals could really be marketed as a racemate or a mixture of enantiomers without really testing all isomers to see how they interact with the body. And so since that time, there's been much stricter controls over how you test the various isomers of a molecule before you can put it onto market. So when we look at enantiomers, the physical properties of chiral molecules are generally the same. So one mirror image, the left-hand molecule, is going to have very, not very similar, but the same properties as the right-hand mirror image in many situations. So the melting point will be the same. The boiling point will be the same. The optical rotations will be the same in magnitude, but in opposite directions. So if one enantiomer rotates plane polarized light by specific rotation of minus 45 degrees, then the other enantiomer will rotate at plus 45 degrees. The chemistry of enantiomers is also very much the same, or exactly the same with achiral reagents. So we need to have a chiral environment for there to be any difference between enantiomers. So how do we really sort of denote the difference between these things? The D and L, plus or minus notation, is an empirical observation. So we put plane polarized light through a sample, we measure a rotation, but we can't predict what that is, and we can't tell anything about what is the actual three-dimensional arrangement of atoms within that molecule. So we need a way to talk about the stereochemistry of a molecule when we just know the structure of it. So that's a topic for another video. We're going to talk about that in another video, and that relies on a series of rules called the Carnegie-Prolog rules, and we're going to assign letters to one enantiomer or the other based on their chirality. Okay, so that's a brief introduction to stereoisomers, and particularly chirality and enantiomers in organic chemistry. Thanks for watching.